Good morning to all. In this session, we are going to discuss about CSIR NEET GRF Chemical Science June 2016 Part C Series 2, where we are going to cover 10 questions in this series. Okay. So already we have been completed 2018, 19, 20 CSIR Chemical Science question papers of both the sessions, including June and December, and even 2017 June 2016 June Part B session also completed. Now we entered into Part C. So we made into different series in order to avoid the ambiguity of lengthy videos. That's why each series consists of only 10 questions. This kind of previous year question paper discussion will helpful for your competitive exams and also entrance examinations. So let us see today's question paper, that is series series 2 is going to be discussed now. Here question number 81 to 90 will be discussed in this session. Let us see. It will be series 2. In series 2, question number 81 to 90 are going to be discussed. Right. So here 71 to 80 questions are going to be discussed in the series 2 Part C CSIR NEET GRF Chemical Science June 2016. Let us go to question number 81. Proton NMR spectrum of ruthenium neta-4 C8H8CO taken thrice at 23 degrees centigrade consists of sharp single line. The number of signals observed at low temperature minus 140 degrees centigrade in its spectrum is. It is a part of proton NMR spectrum of inorganic complex. Ruthenium complex is provided to us, and here the polydentate ligand is cyclooctatetraene. Even here we have eight electron system, all are in conjugation. Only 4 electrons are contributed towards this coordinate covalent bond with this ruthenium. At 23 degrees centigrade, it able to give only single line because all the bonds are identical, and there is a delocalization of pi electrons. If delocalization of pi electrons are possible, all the bonds becomes identical and all hydrogens will appear at only one set of hydrogen NMR spectrum, give only single line. But when we apply the temperature of minus 140, extremely lower temperature can be applied. At this stage, what happens? Bond becomes stagnant. They will not participate in any kind of resonance, so that here fixed number of signals, different number of signals will be appeared. The molecule becomes rigid at this minus 140 degrees centigrade. At that rigid condition, we can't expect fluxionality in the molecule, so that there is a possibility of different set of protons and a different set of NMR signals will be appeared. Let us see how many possibilities are there. If you are taking this ruthenium complex with the cyclooctatetraene, it is indicated as neta-4. Neta-4 means only 2 pi bonds are participating in this bonding with ruthenium. Remaining 2 bonds are left as a free only. Right here, that's the reason why we are making the numbering in cyclooctatetraene in this manner. 1, 2, 3, 4 is given for one side. 1 prime, 2 prime, 3 prime, 4 prime is given for any other side. Okay, so we have to depict this under normal condition at 0. That means 23 degrees centigrade. What happens at room temperature? All bonds are equally delocalized, so that all the protons are equivalent. Hence, we can say all are giving only single signal. But we are employing minus 140, so that there is a possibility of fixed rigid nature. At that rigid nature, if we go for 1-2 shift. So 1-2 shift in the sense here, this pi electrons will be participate in the shifting in this manner. So in between 1, 2, 3, 4, in between these two pi bonds will be there. Remaining 4, 4 dash and 2 dash, 3 dash will left with unreacted pi bonds. So here this kind of resonating system will participating in bonding where 1-2 shift is observed. So if we go with 1-3 shift within the molecule, if 1-3 shift is observed here, slightly this is migrated towards, this is extended towards next center, so that you can observe bonds in between 1 prime, 2 prime and 3 prime, 4 prime pi bonds which are not participating will be there. And in between 1, 2, 3, 4, these bonds are participating in bonding with ruthenium. This is known as 1-3. In the similar manner, 1-4 will be there, and even 1-5 shift is also there, where we can find 3, 4, 4 dash, 3 dash electrons will participating in bonding, and 1 to 1 prime, 2 prime bonds are free in nature. They are not participating any bonding with the central metal, right? So in this manner, here 4 kind of shifts are possible, and 4 different possibilities, 4 different arrangements are found. That's why each kind of arrangement contribute one kind of signal. The total possible signals will be 4 types because of 1-2 shift, 1-3 shift, 1-4 and even 1-5 shift. So here 4 signals will be appeared at -140. For question number 81, option number 3 is the correct answer. Let us move on to question number 82. Here, the G value for cerium plus 3,4F1 and praseodymium plus 3,4F2 are respectively. G factor to be predicted. We have the empirical formula in order to predict the G value. G is equal to 1 plus S into S plus 1 minus L into L plus 1 plus J into J plus 1 by 2J into J plus 1. This is the empirical formula in order to calculate G factor. In order to get all these, S spin value is needed, L angular momentum quantum number, J it is the factor which is calculated from L and S. So these 3 parameters are needed to be predicted. First, 2 elements are given. One is cerium plus 3 being it is 4F1 system, praseodymium plus 3 being it is 4F2 system. Let us arrange these electrons in F orbital. Cerium plus 3 4F1. So the F orbital of 7 F orbital having 7 subshells in that, and only 1 electron will be present in cerium plus 3. So its magnetic angular quantum moment number is given as +3 +2 +1, 0 -1 -2 -3. If 1 electron present in this first one, it contribute +3. L value will be +3, and 1 electron is there which contributed half, right? So S value is half, L value is 3. Then J value for less than half filled, L minus S. If more than half filled, L plus S. It is a kind of only F1 comes under less than half filled, so that we have to take L minus S value. L is 3, S is half. 3 minus half, it will be 5/2. S is known, L is known, J is known. Then let us substitute in the G factor value 1 plus S is 1/2, 1/2 plus 1, L is minus, L is 3, 3 plus 1 plus J is 5/2 into 5/2 plus 1 by 2J into J plus 1, 2 into 5/2 into 5/2 plus 1. If we substitute all the values, go for the calculation. G can be calculated as 6/10. We can apply Bodemar's formula here, and based on that we can go with the calculation, and the G value is predicted as 6/7 for cerium plus 3. The second one will be praseodymium plus 3, where 2 electrons are there in the F shell, and +3 +2 orbitals are contributing 2 electrons. So each electron spin, half plus half spin will become 1. Now L value +3 +2, it will become 5. So J value L minus S, 5 minus 1, it will become 4. Then formula same, that is 1 plus S into S plus 1 minus L into L plus 1 plus J into J plus 1 by 2J into J plus 1. When we substitute S, L, J values in the equation, 1 into 1 plus 1 minus 5 into 5 plus 1 plus 4 into 4 plus 1 by 2 into 4 plus 1. If we substitute all the values and go with the calculation of all these, G is calculated as 4/5. 4 by 5 for praseodymium, 6 by 7 for cerium. 6 by 7 cerium, 4 by 5 praseodymium. That is given in option number 4. For question number 82, option number 4 is the correct answer. Let us move on to question number 83. The room temperature magnetic moment for monoatomic copper plus 2 effective complex greater than 1.73. This may be explained using the expression. Here, magnetic moment can be calculated by 3 different empirical formulas. Only spin is contributing magnetic moment, then the formula will be under root 4s into s plus 1. If spin orbit both are coupling, in that case mu s plus l can be calculated as under root 4s into s plus 1 plus l into l plus 1 Bohr magnetons. This is the formula for spin orbit coupling. But exceptionally, in some other cases, there is a deviation. In that case, there is a deviation for spin only formula, so that mu effective becomes mu s into 1 plus alpha lambda by delta. So something can be multiplied with mu s, something can be multiplied with mu s. That's the reason why. So spin only value will be 1.73. For copper plus 2, it will be more than 1.73 because we are multiplying mu s with some other integer value, right? That's why it will be greater than this term. That is purely explained by taking the formula mu effective is equal to mu s into 1 minus alpha lambda by delta. So for question number 83, option number 1 will be the correct answer. Now let us move on to question number 84. It is the kind of inorganic chemistry, borane chemistry, where the number of 3 center 2 electron bonds present in the aluminium BH4 taken thrice is. Here central metal is aluminium. Around aluminium we have borane unit that is represented in the structure. Here boron is surrounded with BH4 units. 3 BH4 units are present in this manner. They're asking for how many 3 center 2 electron bonds are there. If you are considering one bond, one atom bounded to another atom, which are bonded by one bond, for example, in this case, 2 atoms contributed with 2 electrons. This is said to be 2 centered 2 electron bond. Means 2 atoms combined with 2 electrons. That is a natural bond formation, natural covalent bond formation. But exceptionally, in some conditions, they participate in contribution. That means bridging. Means so 3 atoms are participate. 3 atoms are sharing only 2 electrons because of deficiency. 3 atoms are able to share 2 electrons among them. The one of the bridge head atom used to contribute. Sometimes electron will remains in between these two, and some other time electron remains in between these two. That kind of bridging nature will be there whenever electron deficiency is observed in that. So such electron deficient 3 center 2 electron bonds in this aluminium BH4 taken thrice are 1, 2, 3, 4, 5, 6. Okay, so 6 bonds are present. So among boron, hydrogen, aluminium, how many atoms are there? Boron is 1 atom, hydrogen is 2 atom, aluminium 3rd atom. 3 atoms are there. If 3 atoms are there, 2 bonds are there. How many electrons should be there? 4 electrons should be there in general. But here, instead of 4 electrons, only 2 electrons will be there. Sometimes these 2 electrons present between BH, some other time these 2 electrons present between ALH. So this is called 3 center 2 electron bond, electron deficient nature. How many are there? 1, 2, 3, 4, 5, 6 bonds are there. So in this AlBH4 taken thrice, 6 such a 3 center 2 electron bonds are present. For question number 84, option 3 is the correct answer. Let us move on to question number 85. The number of skeletal electrons present in the compound carborane C2B3H5, C2B4H6. This is a borane B5H9 respectively. Total skeletal electron count should be predicted. First, let us go with compound number 1, C2B3H5. In order to predict this total skeletal electron, how many CH units are there, how many BH units are there, we have to differentiate. Okay, here CH units are 2, BH units are 3. So total hydrogen count will be 2 plus 3, it will be 5. Entire carbon, hydrogen, boron count got balanced. 2 CH units are there and 3 BH units are present in this. Actually, carbon valency is 4. When it is in contact with hydrogen, total valency will become 3. Right? So 2 into 3 plus. So 3 into boron valence is 3, being it is associated with hydrogen, its valency reduced to 2. BH valency will become 2. So 3 into 2 it will be. 2 into 3 plus 3 into 2, total skeletal electron count will be 12. So for this C2B3H5, total skeletal electrons will be 12. Let us go with second carborane, C2B4H6. 2 CH units are there, 4 BH units are there. Each CH unit contribute 3, each BH unit contribute 2. So 2 into 3 plus 4 into 2. 6 plus 8, it will be 14. 14 skeletal electrons found in this carborane. Now let us go with B5H9. 5 BH units are there. After 5 BH, more 4 hydrogens will be there. They are presented in this manner, 5 into BH plus 4 into H. Each BH contribute 2, right? So 5 into 2 plus 4. Hydrogen contribute only 1 electron. So that 5 into 2 plus 4. So 10 plus 4, it will be 14. So skeletal electrons of B5H9 will be 14. So for compound number 1, 12, compound number 2, 14, compound number 3, 14. 12, 14, 14 given in option number 2. For question number 85, option number 2 is the correct answer. Let us move on to question number 86. It is a part of, again, inorganic chemistry, where EPR spectrum, that means spectroscopic application of inorganic chemistry, can be given. Identify the correct statement for EPR spectrum of vanadium oxy ACAC taken twice, where ACAC stands for acetyl acetinato ligand. It is the bidentate ligand with the square pyramidal geometry at the vanadium. At 77 Kelvin temperature, and the angular momentum of vanadium 51 is given by 7/2. How many EPR signals are given for this vanadium OACAC taken twice? We have to predict. Okay, so for that purpose, we have the geometry here. Vanadium double bond O, CH2, CH2, CH2O, acetyl acetinato. Here also acetyl acetinato ligand is there. This is called a square pyramidal geometry, right? So here 4s2 3d3 is the outer shell configuration under normal zero oxidation state. So when it is bounded with acetyl acetinato, vanadium oxidation state is +4. So means 4 electrons can be discarded. So it will become D1 system, 4s0. 4s0 D1 will be there because 4 electrons will be removed from the outer shell. Now, D1 system, being it is a square pyramidal, symmetry is absent in this. So it is attributed with the 2G values. So it is in anisotropic manner. One side, when we observe the molecule of top side, it is associated with double bond O. At bottom side, double bond O is not there, symmetry is not there within the molecule. Hence, we can say anisotropic effect is there. So in one dimension, one properties, in another dimension, another properties are there, right? That's the reason why for two different dimensions, 2 different G values will be there for this vanadium acetyl acetinato complex. So 2 type of G values are there. Now let us predict EPR spectral lines. The formula will be 2Ni plus 1. Angular momentum value will be 7/4. 2 into, how many vanadium atoms are there in the complex? Only 1 vanadium atom. 2 into 1 into 7/3. I value is 7/3 plus 1. 2 into 1 into 7/2 plus 1. 2 get cancelled, 7 plus 1, it will become 8 lines. EPR spectrum will give 8 lines for one kind of orientation. But here we have 2 orientations, right? Being it is anisotropic. So 2 G values will be there. For that 2 G values corresponding, 2 different set of spectral lines are possible, each consisting 8 lines, right? So it have 2 J values is the correct statement. 2 patterns will be attributed with 8 lines each. So this D statement, A statement, both are correct. A, D statements are given in the option number 1. For question number 86, option number 1 is the correct answer. Let us move on to question number 87. The number of lines showed by BH3 part of molecule PPH3, BH3 taken 11 in the H1 and B11 NMR spectra respectively. Angular momentum of B11 is given by 3/2. Angular momentum of P31 is given by 1/2. For this, how many lines are possible for BH3 part? We have to predict. In 2 different spectra, one is proton NMR, second is B11 NMR. For that purpose, this is the Chemical structure of BH3 PPH3 taken thrice, triphenylphosphine, and this is a borane unit. Both are bonded with BP bond. When we apply proton NMR for B11, the formula will be 2Ni plus 1. How many boron atoms are there? Only one boron atom. 2 into 1. I value for boron will be 3 by 2. 2 get cancelled. 3 plus 1, it will become 4. 2Ni plus 1 formula. So 4 spectral line corresponds to boron 11 in proton NMR. Then proton NMR applied for phosphorus also. 2Ni plus 1. So N is how many phosphorus atom? Only one phosphorus atom is there. Each phosphorus I value will be half. 2 into 1 into 1 by 2 plus 1. 2 get cancelled. 1 plus 1, it will be 2, right? Proton NMR data for B11 will be 4. For phosphorus, it will be 2. 4 into 2, total spectral lines will be 8. Let us apply B11 NMR also. They are asking for proton as well as B11 NMR. B11 NMR, B11H1 will be there and B11P31 interaction also there. Here, in order to predict the spectral lines for proton, so how many protons are there in the compound? 3 are there. Each proton attributed with half. I value will be half. So 2 into how many hydrogens? 3 into each hydrogen I value will be 1 by 2 plus 1. 2 into 3 into 1 by 2 plus half plus 1. So 2 get cancelled. 3 plus 1, it will become 4. Then 2Ni plus formula, 2Ni plus 1 formula also applied to this phosphorus in B11 in. Then how many phosphorus atom? Only 1. So 2 into 1 into phosphorus angular momentum is 1 by 2 plus 1. 2 get cancelled. 1 plus 1, it will be 2. 4 into 2, 8. So proton NMR gives 8 lines. B11 NMR also gives 8 lines. So 8 and 8 is the correct answer. For question number 87, answer number 1 is the correct answer. Let us move on to question number 88. To record mass bar spectrum of iron containing sample, a source X is used. Iron is the product here. We have to go with the starting material X. X after nuclear transformation Y gives gamma radiation used in mass bar spectroscopy. X and Y respectively. Okay. Here it is very clear that X should be obtained from iron should be obtained from X. So this X is emitting gamma radiation after converting into this iron, right? So initially X was taken, so that should be converted into iron. For that purpose, here only the probability will be cobalt 57 should be taken as the X. It will be the starting material. When cobalt 57 is a starting material, it participates in electron capture. When electron capture is possible, electron is associated with mass number of 0 and atomic number, so -1 will be there. That's why when cobalt accepting electron, its atomic number will be descended by 1 unit. Atomic number will be decreased by 1 unit. Cobalt 27, it turned into 26 atomic number. What is 26 atomic number element? Iron. Now, atomic mass, electron is not having any mass, right? So that electron when accepted by this cobalt 57 remains as 57 only. So after getting this iron isotope 57, that is nuclear transformation. During that reaction, gamma emission is possible. Let us write in the equation form. We are taking cobalt that is attributed with cobalt 57 and atomic number. What is the atomic number of cobalt? 27. Now it is added with electron capture. So we are adding electron to this cobalt. This will be the starting material. Cobalt will be the starting material and accepting electron here. After accepting electron, what happens? Its atomic number is reduced by 1 unit, but mass number will not be changed. So atomic number 26 corresponds to what? Iron, right? Atomic number 26 corresponds to iron. So that's why the product generated will be iron. The product generated will be iron, and being it is accepting electron, so that mass number will not be varied. 57 mass number remains as such only. And along with this, some extent of radiation, that is gamma radiation will be emitted. This is the probable reaction, right? In this, starting material will be cobalt 57 and it participated in electron capture, so that final product iron will be generated. This is called mass bar effect, right? So cobalt 57 electron capture. For question number 88, option number 3 is the correct answer. Now let us move on to question number 89. Correct combination of number and size of rings present in the metal ion porphyrin complex. So the best example for central metal with porphyrin ring system will be hemoglobin. Hemoglobin iron bounded porphyrin system will be there. Here porphyrin system is represented in the structure. Central metal will be iron and it is surrounded with pyrrole rings and also another 6-membered rings are present within the structure. So here iron surrounded with the pyrrole. How many pyrrole units are there? 1, 2, 3, 4 pyrrole units are there, and the 6-membered rings. Here you can find also 6-membered rings also. 1, 2, 3, 4 6-membered rings are present. 4 5-membered rings, 4 6-membered rings are there in this porphyrin ring. So 4 5-membered and 4 6-membered is the correct answer. For question number 89, option number 1 will be the correct answer. Let us move on to question number 90. In the human body, cisplatin hydrolyzes to di-aqua complex and modifies DNA structure by binding to. So the purpose of cisplatin is it is the anti-tumor agent, anti-cancer agent. Whenever it entered into the body, first it mixed up with water. When it mixed with water, 2-chloro now converted into di-aquo. So di-aquo complex will be formed. Now it is in contact with DNA. DNA structure will be like this. Double helical structure will be there. Platinum will bound to this di-aquo complex of platinum will bound to DNA in this manner, where this guanidine base. So nitrogen of 7 guanidine base will be attached to this one. So this guanidine base of DNA will be bounded to this cisplatin in this manner. So guanidine of N7 position will be bounded. So nitrogen atom of guanine base will be added. So for question number 90, option number 1 is the correct answer. Cisplatin, that is the cancer agent. When cisplatin first hydrolyzed, what happens? 2-chloro now replaced with diaquo. When it is bounded to DNA, so here platinum bounded to DNA in this manner, guanine base of DNA double helical structure will be bounded to this one, so that change in the structure is possible. So for question number 90, option number 1 is the correct answer. By this, we successfully completed the series 2 of Part C, June 2016 CSIR NEET GRF Chemical Science. Thank you very much for your patience listening. Thank you one and all.